The purpose of this video is to cover cipher-trust transparent encryption for Kubernetes. So fundamentally, Kubernetes is about orchestration of a container environment and container resources. One of those resources being storage. Now, if you have a sensitive application that's storing sensitive data in that storage, the idea is to use transparent encryption to provide encryption and access control for that data. Let me give you an example. So in my environment, I have an NFS server. I'm currently exporting two shares. There's the NFS data secret and NFS data public. Now, currently those directories are empty, but I'm going to demonstrate how using Kubernetes and using this volume or this share as a data storage area leaves you vulnerable to certain types of attacks at the storage layer or attacks within the pod layer. But if you implement transparent encryption for Kubernetes, then you can both encrypt the data store and provide additional access controls to that data store. So in this data store, you could have sensitive data files. They could be image files, text documents, or it could be database data files. It could be a Postgres or MySQL or some other database that you have a persistent storage for. Let me quickly show you that these are either empty or going to be empty directories. That one is empty. So you can see that both of these shares are empty of data currently. Alright, I'm going to go out to my Kubernetes environment. We're going to start off with creating a persistent volume that maps to the public share, and a claim, or PVC, persistent volume claim, to that share, and then a pod that then uses that claim. Let's quickly look at the definition of those objects. So this is my persistent volume definition. Okay, this is the name of the object, NFS public PV for persistent volume. The protocol that's being used is NFS, and this is my share path, and this is my share server. So fundamentally, I'm defining the NFS share as a object to orchestrate by Kubernetes. I have alias the kubectl command as K. So if I issue the command K, that's really kubectl. Apply the file. And I've created the persistent volume. And I can see that persistent volume resource. Now let's look at the claim. And so what is it? This is the object type. It's a persistent volume claim, and the name of the resource is going to be NFS public PVC. The storage class is NFS, and the rest are just details about size and space, but it's essentially saying I'm going to use this claim and I'm going to use this type of storage class as the semantics for accessing that object class. Okay, I now have the persistent volume claim to work with. So now let's look at the pod definition. Okay, it's the type of course is pod, which is a container. This is the name of the pod once created. This is the definition of a data volume that I'm going to be using. It's going to be using my claim, which is NFS public PVC. Okay. It's going to, of course, that claim type is of NFS, so it's going to mount that underlying claim and corresponding volume to the public directory within the pod, right? And that's the name of the mount within the pod, and that's the, of course, the location of where the data is actually going. So this is just a basic way of setting up a pod. And of course, the image type is a Ubuntu. It's just a basic Ubuntu image. Okay, it's already active and running. So now I can go inside that container and in this case I'm going to be running bash, which gives me a shell window, but I could do almost anything. I could execute any kind of command that exists within that pod itself. In this case, this will open up a shell window for me. So now I am in the pod itself. I'm within the container. So if I do an ls, I am listing the directories and files of the information that's inside the container itself. So if I go to the public directory, then I'm accessing that container's NFS data store. Currently there's nothing in there, so let me create just a little bit of data there. I'm going to create a file from that. So I have a file with hello world in it, and the file name is hello.txt. So if I go back out to my NFS server, and I go to the public directory, I can see that file on the NFS server, and I can see the data. So there's nothing secure about it. It's all unencrypted, no access control at all, either within the pod or within the data store, because the data is all in clear text. Now, so what if this was data that's sensitive in nature, right? User IDs, passwords, credit card information, whatever I would consider sensitive. Well, Cipher Trust transparent encryption for Kubernetes gives you the ability to not only apply encryption to this data, but also security controls within the pod environment. So let me show you how to do that. To start the process, we need to obtain the CipherTrust Transparent Encryption Agent for Kubernetes, which is maintained in a GitHub repository. So we'll clone the repository using git. And when we do that, we get this repository copy of the project. So if we go into that project, there's a deploy.sh script that we need to run on the environment. So it'll use it's actually a Helm chart, so you need to have Helm installed, but it will create the necessary objects within the Kubernetes landscape to support the encryption and access control of data within the environment. Once it's deployed, then you get some additional services running in Kubernetes. To do that, all I have to do is query the Kubernetes environment. And you can see an additional node and controller objects that are running in the environment. And on Software Trust Manager, we need to create the security objects that are implementing the security controls. First, we need to create a policy. And the type of policy is going to be CTE for Kubernetes. Now, I'm not going to cover how the transparent encryption policies work. They effectively work the same way as other transparent encryption policies. You're defining access control of data that implements a key, so you encrypt data that's created and unencrypt data that's being read or accessed. The first rule we'll create is the permit apply key rule. And then the next rule will be the deny rule. So no real access controls I'm applying here. You can review other videos on how to set up transparent encryption rules. The thing to note is the rules you define where you're granting access to users or you're granting or denying access to processes. This enforcement is taking place within the pods or containers that you're applying to. So if you grant a specific process or user access to data inside the environment, the enforcement takes place inside the actual container pod. I'm going to create a new key during this process. It is an AS256-bit key. And here's a summary of my policy. Policy has just two rules. Permit and apply key essentially for everything. Again, no access controls actually being forced. I'll demonstrate the encryption from the NFS server. And then we're in a deny rule, and we're going to be using this key. Okay, now I have a policy. Let's make note of that policy name. The next thing we need to do is create a storage group. And a part of creating the storage group, you need to define what is the namespace within the Kubernetes environment where the storage group is going to be used. Well, I'm going to be using the default namespace. And then I'm going to be creating a storage class that defines the behavior for the storage in that namespace. And we'll make note of those. So now that I have a storage group defined, I need to create a guard policy inside the storage group. And of course, I'm going to use the policy I created in the previous step. And now this part of the setup is complete. I do need one more component, which is a registration token. And this basically is a secret such that when a CTE for Kubernetes client attempts to contact Cipher Trust Manager, if it knows this secret, then we'll accept the registration of that client to this host. Now we'll need to tell Kubernetes about this secret. And so there is a component within Kubernetes to store secrets. So, but we need this secret to be base 64 encoded. So just choose this option and then copy the secret. And we'll make note of that information as well, because we'll need it later in our definitions of our Kubernetes objects. Okay, that's all we need to do on the CipherTrust Manager side. I'll make a quick note of the Kubernetes clients. There's no Kubernetes clients currently, and that is because when a Kubernetes pod is created that uses the storage group and the corresponding storage class, that pod is going to be dynamically registered with CipherTrust Manager. So it is completely a dynamic environment. So let's go back out to our CipherTrust, or excuse me, let's go back out to our Kubernetes environment. And look at our configuration files. Alright, the general order is we're going to create the persistent volume and then the claim on that volume. These are the ones we did in the previous set of samples, but we'll be using the secret NFS share. So you can see in this situation, it's just a persistent volume. The it's of type NFS, so it's an NFS share type, and it's going to point to our share that is in the secret directory under the share data, and there's my NFS server. So I now have a new persistent volume, secret. And here is my persistent volume claim to the persistent volume that I defined earlier, which basically just says this claim is of type NFS, and once I map it to that other persistent volume, I can then use a pod to contact this persistent volume, use the NFS protocol to access that volume. But I'm going to establish an intermediate transparent encryption claim such that will implement encryption when this claim is actually used. So now I have a persistent volume claim for my NFS persistent volume. Now I'm going to create the secret. Again, this is the secret that's going to be used in the self-registration of the transparent encryption clients with CipherTrust Manager. So I'm going to take my registration token that I copied, so I'm creating a Kubernetes secret. This is the name of the secret, and this is the secret that's actually being stored. And so now I've created a new Kubernetes secret. So now I'm going to create my storage class. So in this storage class, I give a Kubernetes name. I specify where the Cipher Trust Manager is, which is just its IP address. I need to identify the storage group, and I need to identify what the secret is for registration. So now I have a storage class defined. Okay. The next thing is to create my claim. This claim will implement the storage class. So I give the claim a name. I specify the policy within the storage group. What is being mapped? So this claim is going to be mapped to this claim, and then I'm implementing this storage class. Okay, so I now have a new claim, and again, this claim is implementing the Kubernetes storage class, and the underlying storage is this claim, and naturally this claim points to the NFS secret share. So now I have a claim. I can now create a pod. So I'm going to give the pod a name. It's pointing to the persistent volume claim. This is my mount path. I'm defining the name of a volume is secret. So these two have to match up because this is defining the details of this volume. So this claim is going to be represented as access to a directory structure. In this case, it's going to be NFS, but the directory structure where data is going to be stored is in this secret directory. Okay, so the container has started its creation process. And it's going to take a second because it needs to download the image, and then after the image is downloaded, it needs to mount the file systems, and then after mounting the file systems, it needs to further process the creation of registration to Cipher Trust Manager. Okay, and now it's complete. Once you get to a ready state, you're now ready to go. So let's get inside that pod itself. So I am now within the container. I now have a directory called secret. It's empty. Okay, so now I've put some data in a file. We'll go out to the actual NFS server, and I can see my secret text that I created here. But if I look at the data now, you can see that it is all encrypted. And so the security policy is enforcing whether I have one pod or 10 pods, as long as it's implementing that security group and the storage class underneath the covers. All the data access within those containers will have the enforcement of the policy rules, which is encrypt and decrypt. And of course, if you have other access control definitions, then those would be enforced.